Imagine a world where the heat is relentless, with no escape from scorching summers, where food spoils within hours and life-saving medicines can't stay cool. For most of human history, this was the harsh reality, until scientists discovered a groundbreaking solution: Freon. It seemed like the perfect fix for cooling problems, but it carried serious, unforeseen consequences. Freon refers to a group of chemicals known as chlorofluorocarbons, CFCs. These compounds consist of carbon, fluorine, and chlorine, and belong to a larger family of chemicals called halocarbons. The most famous of these is Freon 12, or dichlorodifluoromethane. Before Freon, early systems used dangerous gases like ammonia, methyl chloride, and sulfur dioxide, which were toxic and sometimes fatal if leaked. In 1928, Thomas Migley Jr., working for General Motors, developed Freon as a non-toxic, non-flammable alternative. Its chemical stability made it ideal for refrigeration, air conditioning, and aerosol propellants. It works through phase transitions. When a liquid evaporates, it absorbs heat, and when it condenses back into a liquid, it releases heat. In a refrigeration system, Freon cycles between liquid and gas states, efficiently transferring heat from one place to another. By the mid-20th century, Freon was ubiquitous. It was used in refrigerators, air conditioners, aerosol sprays, and even as a propellant in medical inhalers. Its odorless, stable, and effective properties quickly made it the industry standard. Its widespread use revolutionized industries, enabling food to be stored safely for longer periods, allowing homes and businesses to stay cool in hot climates, and making products easier to dispense in aerosol form. It was also used in industrial applications, such as cleaning electronic components and expanding foam plastics. However, while its use became widespread, the compound was silently contributing to an invisible environmental issue, one that wouldn't be fully understood until decades later. In the 1970s, scientists made an alarming discovery. Earth's ozone layer was thinning. The ozone layer is a protective shield in the stratosphere that absorbs harmful ultraviolet radiation from the sun. Without it, the planet is exposed to higher levels of UV radiation, which increases the risk of skin cancer, cataracts, and ecosystem damage. When CFCs are released, they aren't broken down in the troposphere and instead slowly drift into the stratosphere over several years. Once in the stratosphere, ultraviolet radiation breaks down CFC molecules, releasing chlorine atoms. These chlorine atoms act as catalysts, breaking down ozone molecules into oxygen gas and individual oxygen atoms. A single chlorine atom can destroy over 100,000 ozone molecules. This process contributed to the formation of the ozone hole over Antarctica, which was first confirmed in the 1980s. As the hole expanded, scientists warned that continued CFC emissions could lead to severe global consequences, such as increased UV radiation exposure, disruption of weather patterns, and damage to agricultural production. Without intervention, the problem would only worsen. Recognizing the danger, scientists and governments acted quickly. In 1987, the Montreal Protocol was signed, an international treaty aimed at phasing out the production of CFCs. It became one of the most successful environmental agreements in history, with countries worldwide committing to reduce and eventually eliminate their use. As a result of the Montreal Protocol, CFC production dropped dramatically and ozone levels began to stabilize. Studies showed that the ozone layer was slowly repairing itself, and by the early 2000s, scientists confirmed that the ozone hole over Antarctica was shrinking. If recovery continues, ozone levels are expected to return to pre-1980 conditions by the middle of this century. This marked a rare instance where global cooperation effectively addressed an environmental crisis. But banning CFCs came with a new problem. What do we replace them with? Enter HFCs, hydrofluorocarbons, which had similar cooling properties but did not contain chlorine, meaning they did not deplete the ozone layer. They quickly became the new standard for refrigeration and air conditioning. While HFCs solved the ozone problem, they introduced a new environmental issue. These compounds are potent greenhouse gases, with some having thousands of times the heat-trapping ability of carbon dioxide. To address this, scientists have been developing even better alternatives. One promising solution is hydrofluoroolefins, HFO, which break down much more quickly in the atmosphere and have a low global warming potential. Additionally, some industries have turned to natural refrigerants like carbon dioxide, ammonia, and hydrocarbons, which have minimal environmental impact and are highly energy efficient. The transition to these newer compounds is still ongoing, but the hope is that future refrigerants will allow us to stay cool without warming the planet. Freon started as a life-saving invention, but over time, it became clear that even the most revolutionary breakthroughs can have unintended consequences. The history of Freon highlights how scientific progress can bring both benefits and risks. What other chemicals do you think have changed the world, for better or worse? Let me know in the comments. If you enjoyed this video, don't forget to like and subscribe for more in-depth looks into the science that shapes our world. And we'll see you in the next video.